Causal thinking is one of the defining features of human intelligence. It allows us to move beyond mere perception, beyond what we see, to understand why things happen. Why does a glass fall when a laptop is removed? Why does a bookshelf collapse if its supporting shelf is taken away? These are not just spatial questions, they are causal ones. And while modern vision language models can detect objects and describe scenes, they struggle to uncover these deeper cause and effect relationships. To bridge this gap, we introduce visual causal discovery, a new task that challenges models to infer not just what is present, but how entities interact through causal mechanisms. This requires more than pattern recognition. It demands counterfactual reasoning, the ability to imagine what would happen if one entity were removed or altered. It demands an understanding of intervention, not just observation. To make this possible, we first built the Visual Causal Graph dataset, VCG32K, the largest and most comprehensive dataset of its kind, with over 32,000 images annotated with entity-level causal graphs. Each image comes with refined bounding boxes, precise entity labels, and explicitly annotated causal relationships such as support, carry, or lift. These annotations are grounded in the formal definition of causality. A relationship exists if removing the cause would disrupt the effect's current state. But data alone isn't enough. We needed a model capable of reasoning through these complex interactions. So we developed CauSight, a novel vision language model designed specifically for visual causal discovery. Unlike standard models that rely on static scene graphs, CauSight learns to generate dynamic, interpretable causal graphs by simulating a chain of reasoning steps, what we call the Tree-of-Causal-Thought, ToCT. Here is how it works. ToCT uses a teacher model, QN2, 5VL72B, to autonomously generate high-quality reasoning trajectories. The model performs three key actions in a loop: region selection, entity recognition, and causality orientation. It zooms into promising subregions, identifies candidate entity pairs, and then applies the causal criteria: direct contact, state maintenance, and counterfactual disruption. This process is guided by Monte Carlo tree search, MCTS, which explores multiple reasoning paths, evaluates their quality, and selects the most promising ones. The result? A curated set of reasoning trajectories, each a step-by-step narrative of how a model deduces causal structure. We filter these trajectories to keep only those that outperform simple one-step reasoning, ensuring the model learns from high-quality, effective strategies. With this foundation, we train CauSight through a multi-stage pipeline. First, we use supervised fine-tuning on the filtered ToCT trajectories, instilling a structured reasoning policy. Then we apply reinforcement learning using the Group Relative Policy Optimization, GRPO, algorithm, guided by a custom graph-based causal reward. This reward is designed to maximize both recall and precision in causal graph reconstruction. It encourages the model to find all true causal edges while minimizing false positives. It also includes a format compliance term, ensuring outputs are structured and consistent. The results? A breakthrough in visual causal reasoning. On the VCG32K benchmark, CauSight achieves a graph recall of 34.2%, a 21% absolute improvement over GPT-4.1, and over threefold better performance than previous open-source models. Even on the cross-dataset test set, Objects 365, CauSight maintains strong generalization with a 16% recall boost over the SFT baseline. But what makes this performance so significant? It's not just about numbers. It's about reasoning. We analyze the reasoning-induced performance loss, the gap between what a model could achieve with perfect detection and its actual causal reasoning. While models like GPT-4.1 and QN2, 5VL72B achieve high recall, they suffer from massive reasoning gaps, over 20% loss toward their theoretical upper bound. CauSight reduces this loss to just 8%, proving it doesn't just memorize patterns, it reasons. We also evaluated detection stability using the Recall Stability Index, RSI. Models that rely solely on fine-tuning on ground truth labels show poor stability, highly sensitive to small changes in detection thresholds. CauSight, however, strikes a balance. It improves causal discovery performance while maintaining robust detection, indicating a harmonious integration of perception and reasoning. Ablation studies confirm the importance of each component. Removing ToCT drops recall by 6.7%, and skipping reinforcement learning reduces it by 21.1%. But when both are combined, CauSight achieves a 27.4% gain over the base model, demonstrating that structured reasoning and dynamic feedback are essential for causal understanding. Qualitative analysis reveals even more. While the base model fails completely, and the SFT variant hallucinates spurious relationships, CauSight produces accurate, coherent causal graphs. It correctly identifies that a bench supports a bag, that a table holds a vase, and that removing a support causes collapse. In complex scenes, it even performs attribute-based reasoning, revising incorrect labels, like identifying a chopping board as a table, based on causal context. And beyond the benchmark, CauSight retains strong generalization across domains. On math reasoning tasks like MathV and MathVista, and on visual perception tasks like Blink, it performs comparably to the base model. In contrast, models trained via direct SFT suffer a 20% drop in math reasoning accuracy, highlighting how causal reasoning training preserves broader capabilities. This work marks a shift in vision language modeling. We're moving from models that describe scenes to those that understand them. From passive perception to active causal inference. From answering what is in the image to explaining why it is that way. CauSight is not just a model, it's a new paradigm, learning to supersense. Not just seeing the world, but feeling its mechanisms, predicting its dynamics, and acting with safety and precision. Our code, model, and dataset are fully open-sourced. We invite the research community to build on this foundation, to explore deeper causal structures, and to push toward truly intelligent, general-purpose AI. Because if we want machines to reason like humans, we must teach them not just what to see, but how to think.